Welcome to Ask and Learn.
In this problem, we're given that the gravitational potential V is equal to 20 times x plus y newtons per kilogram in a given region. Now we know that the units, or rather the dimensions of gravitational potential are the dimensions of acceleration that are of length times time raised to the power -2. These numbers are dimensionless, so we don't need to consider their dimensions. Now Newton has the dimensions of mass times length times time raised to the power -2, and the unit kilogram has the dimensions of mass and it's raised to the power -1. So anything raised to the power -1 times itself will cancel out, and that gives us the left hand side as being equal to the right hand side. So it's verified that the equation is dimensionally correct. So part A is done. Now for part B, we need to find the gravitational field at the point. So G is equal to the gradient of V. Now the gradient of V is actually equal to the partial derivative of V with respect to x times the I component plus the partial derivative of y partial derivative of V with respect to y times the j component. And note that there is no z over here, so our field does not have a third component, a k component, so we can leave that out. The partial derivative of our field with respect to x we can simply use. So the partial derivative of our field is simply the partial derivative of 20 times x plus y, and that's being multiplied by the unit vector I. And in similar fashion, we can rewrite the partial derivative of the field with respect to y. That's the j component. Now we can factor out the 20 because that's a constant with respect to the derivative. And we can use the constant multiple rule for derivatives times the I component plus, we can do the same here, so that's the partial derivative of x plus y times the j component. Now the partial derivative of x with respect to x is simply 1, so that's 20 times 1, and the partial derivative of y with respect to x is 0 because y is a constant with respect to the partial derivative. And we can use the same argument here. So the partial derivative of, sorry, this was a y, I don't know why I copied it as an x. So the partial derivative of x with respect to y is 0, while the partial derivative of y with respect to y is 1. So that turns out to be 20 times 0 plus 1j, and this entire thing evaluates to 20i plus 20j. And if you like, you can write 0 times k, the same over here, And that's our answer for the gravitational field. Now note that the field is constant, so it does not depend on the location of the particle at all. So we can take the magnitude of the gravitational force on gravitational field on an object. That will give us the square root of 20 squared plus 20 squared plus 0 squared, and that would give us 20 times the square root of 2 as being equal to g. And the force is actually meters per second squared. So the force is actually equal to the mass times the gravitational field. The mass is 500 grams, and we can convert it into kilograms, so multiplying it by the prefix kilo, rather the inverse of the prefix kilo, and we'll multiply that by 20 times the square root of 2, and that will just give us the force as 10 times the square root of 2 newtons. And g in our previous part was in meters per second squared.